In this lecture, we are going to look at different ways of analyzing the covariance and correlation of stock returns in code. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Let's start by downloading the file sp500close.csv. As you recall, this is the pre-processed dataset where I've kept only the close column and have lined up all the stocks by date. Each column is a different close price, and each row is a different day. Next, we load in the data frame using pd.readcsv. Now let's suppose I want to know the correlation and covariance between the following stocks: Apple, Google, IBM, Netflix, and Starbucks. The first step is to filter all the columns for these symbols. We'll call this new data frame sub. Next, we're going to drop any rows that have all elements as NaN, since these probably correspond to non-trading days. As before, we specify axis equals 0, which means to drop rows and not columns, and we say how equals all, so that it only drops rows where all columns are none, and we say in place equals true, so that the operation is done on our existing data frame. Next, we call the head function to check the resulting data frame. Notice how in this dataset, many of the Google prices are missing. If you prefer to build this dataset using your own data from Yahoo Finance, please feel free to do so. Although keep in mind it doesn't affect the exercise. Next, we're going to calculate the returns for each symbol. Notice how the new columns are simply the symbol concatenated with _prev and _ret. Also note that we didn't have to do this calculation manually, although there is generally no harm in doing so. Next, we create a new data frame, filtering out only the columns that contain the returns that we just created. We call the head function again to check our new data frame. As expected, the first row is NaN. The next step is to plot what is called a scatter matrix. Seaborn has a nice function to do this called pair plot, so we've imported Seaborn and called the pair plot function, passing in the returns data frame. Basically, a scatter matrix works like this. Both the rows and columns correspond to the returns for each stock. On the diagonals, we have the histogram for each return. On the off diagonals, we have a scatter plot of each return versus each other return. So for example, Apple versus Google, Apple versus IBM, Google versus Starbucks, and so forth. Basically, it's a visual representation of the covariance matrix or the correlation matrix. We can see directly from this plot how correlated each of the returns is. Recall from our visualization earlier that a perfectly straight line would be a perfect linear correlation. Something that looks like a circular cloud would mean no correlation, and everything else is in between. So from this plot, we can see that there is a decent amount of linear correlation between Apple and Google. So Apple's number 1 and Google's number 2. So this box right here is Apple versus Google, and you can see there's a bit of linear correlation. We can also see a decent amount of linear correlation between Google and Starbucks and Google and Netflix. So this one's Google and Netflix, this one's Google and Starbucks. And for the others, I don't think the correlation is very clear. Next, let's calculate a few more basic statistics for each return. First, we have the mean, that's rets.mean, and we have the standard deviation, that's rets.std. The next thing I'm going to do is plot the mean returns against the standard deviations. In finance, the standard deviation is one way to think of volatility. This plot helps us see a pretty common phenomenon in finance. We see that this plot generally trends upwards. That is, when the volatility is higher, the return is also higher. Finally, let's calculate the correlation matrix and the covariance matrix. Luckily, these are just single function calls. So first we have rets.core. These results seem to confirm our suspicions from the scatter matrix. The correlation between Google and Apple is pretty high, above 0.4. The correlation between Google and Netflix is also high, also above 0.4. And the correlation between Google and Starbucks is the highest, above 0.45. Next, we do the same thing for the covariance, which is just rets.cov. As expected, these values are very small. Remember that we're taking the standard deviations, which we saw earlier, and squaring them, so we expect these values to be pretty tiny. Because of this, the correlation matrix is slightly more useful because it means all the values are normalized to be between -1 and +1.